வணக்கம். Welcome to NPTEL online course on fractals and multifractal. This course is jointly offered by Dr. M. Prem Prasad from Department of Mathematics, Indian Institute of Technology, Guwahati, Assam, India, and myself, Dr. A. Gowrisankar from Department of Mathematics, School of Advanced Sciences, Vellore Institute of Technology, Vellore, Tamil Nadu, India. When we intend to study the fractal, some classic example often arranged are Cantor set, Sierpinski triangle and Van-Schotz curve. Interestingly, these sets were constructed long before the term fractal was introduced by Professor Benoit B. Mendelbohr in 1975. So, in the first week of this course, let us discuss the construction and geometric property of all the sets and the key property that bring all together in the common umbrella called the fractals. So, let us begin with the history of fractals. In the first week, we will discuss the construction of Cantor set and Sierpinski triangle and Van-Schotz curve, followed by the definition of fractal and fractal dimension. Let us start from the construction of Cantor set. While constructing the Cantor set, let us consider the line segment in the real number system R. This line segment consisting of the unit interval 1, this we can call it as the initiator. Now, this initiator is dividing into 3 equal parts like this one. So, each of which length is same, therefore, the length are 0 to 1 by 3 and 2 by 3 to 1. So, now we will remove the open mid interval of these 3 sub intervals. Now, we removed this open interval 1 by 3 and 2 by 3 in the closed interval 0, 1. Then after the first iteration, one can get 0 to 1 by 3 and 2 by 3 to 1. Now, in the initiator to first step, we will get this 2 interval of length 1 by 3. There are 2 interval of length 1 by 3. Now, we will apply the same process on the first step. Now, we will divide this one as 3 equal parts. Both the interval will divide into 3 equal parts and removing the mid part in the left side as well as in the right side. So, now after this iteration, after the second iteration, one can get 4 interval of length 1 by 9. Again, apply the same process. Here divide each of these 4 interval into 3 equal parts and remove the mid open interval in the 4 interval, then one can get this 8 interval of length, that means 2 power 3 number of interval of size 1 by 3 power 3. So, there are 8 intervals of length 1 by 3 power 3. So, continuing this process, after certain iteration, one can get this type of figure. That means, we will take the intersection of all the interval, then one can get the Cantor set image. This is after certain iteration, finite number of iteration, the picture illustrates the construction process of the Cantor set. Now, let us discuss how this Cantor set is constructed in mathematical form. So, we started with the closed interval 0, 1, we call it as the step initiator, so it is the step 0, so we can name it as C naught. Then after the first interval we have two interval of length 1 by 3, so it is denoted as C1, we are taking the union of these two interval. Then C2 has 4 interval, take the union, and each of the interval size is 1 by 9. Then one can observe from C0, C1, C2 is C0 is larger than C1 and C2, and C1 is larger than C2 and C3. Similarly, C2 is larger than C3, C4 and so on. So this sequence C0, C1, C2, C3 and so on, it is the decreasing sequence, whereas each term is the compact sets. So if you are taking the intersection of all the sets, one can finally arrive the Cantor set. Now we will try to understand what is the nature of Cantor set. For that, let us find the length of the Cantor set. So for the Cantor set, after each iteration we have 2 power n number of interval of size 1 by 3 power n. After the first iteration we have 2 interval of size 1 by 3. So after the nth iteration one can get 2 power n interval of size 3 power n. So this is the decreasing sequence of intervals. Therefore if you are taking the limiting case, we will get the length of the Cantor set which is equal to 0. So literally the length of the Cantor set is 0. Now in each iteration we are removing the certain amount of interval, it has the length. Let us try to calculate how much interval we removed from the closed interval 0, 1 and obtaining the Cantor set C. For that I am just go through the construction process. After the first iteration we removed one interval of size 1 by 3. So this is the interval we removed, open interval we removed, and after in the second iteration we are removing 1, 2. There are 2 interval. What is the size of each interval is 1 by 3 power 2. And here we are removing 4 interval, that means 2 power 2 interval of length 1 by 3 power 3. So after nth iteration one can get 2 power n interval is removed and their length is 1 by 3 power n plus 1. So if you want to calculate the length of the total interval is removed from 0, 1, we need to take the sum of all the removed interval. So if you are taking the sum of all the removed interval, you can get this series form. That means the first iteration we are removing one interval of size 1 by 3, 2 interval of size 1 by 3 power 2, and after that 2 power 2 interval of 1 by 3 power 3 interval is removed. So by doing some simple mathematical calculation, if you are taking 1 by 3 out, we will get this type of series. So one can easily observe here, this is the geometric series of the form 1 plus x power 2 plus and so on. So this geometric series converges to 1 over 1 minus x, only when this number x is modulus of this number x is less than 1. So obviously in our case the 2 by 3 is less than 1, the 2 by 3 is less than 1. Therefore this series convergence to 1 over 1 minus 2 by 3, there is a coefficient 1 by 3 here. So if you are solve this one can get the answer as 1. So what is this 1 represent? In each process, each iteration process, we are removing the certain interval, then finally we calculated the sum of all the interval removed from the closed interval 0, 1. Surprisingly, we are getting the removed total length of the all the removed interval which is equal 1. So, it means that literally we removed all the points from the closed interval 0, 1 and obtained in the Cantor set. Now, this arises a simple question: does Cantor set has the any point or nothing in the Cantor set? Let us try to answer these questions. In the construction of the Cantor set, you can see then the construction of the Cantor set, we started from the closed interval 0, 1. One can observe that in all the iteration, number 0 is appearing in all the iteration. Similarly, number 1 is appearing in the all the iterations. So, therefore, while taking the intersection of all the points, 0 is belongs to the Cantor set C. Similarly, the number 1 is belong to the Cantor set C. And what about number 1 by 3 and 2 by 3, these endpoints? Yes, obviously, the 1 by 3 is belongs to the initiator and all these sets. Therefore, 1 by 3 is also belongs to in the all the iteration, and 2 by 3 is belongs to all the iteration. Whereas, if you are taking any endpoints in the Cantor set, all the endpoints are is a member of the Cantor set. So, we are doing this, the dividing 3 equal parts and removing the mid parts. We are doing this as infinitely many number of times and we are obtaining the Cantor set. Therefore, Cantor set has the infinitely many points. Now, Cantor set has the numbers which is the end point of the each iterations. Now, the question is, does the Cantor set has any number which is not an end point of any of the iterations, or alternatively we can rephrase this sentence. If one can take the number from the Cantor set, what is their representations? So, this question is answered from the following theorem. For that, let me define the some basics number theoretic representation of the real number systems. That means, how to represent the given number in the real number system by the base 3 expansions. Every positive integer x has a unique representation as follows: x can be written as sum of j equal to 0 to m aij 3 power j, where this aij is any one of the number from 0, 1, 2, 3. For instance, if you are taking the number 15, the 15 can be written as 0 times 3 power 0 plus 2 times 3 power 1 plus 1 times 3 power 2. If you are sum all the 3 times, one can get the number 15. So, this construction is very simple. If you want to construct any random number, I will show the how to find the base 3 expansion of number 15. You simply divide the number 15 by 3, then it has the quotient and the remainder. So, the quotient for this term is 5 and the remainder is 0. Therefore, the first term is in the base 3 expansion 0. Then now you can take the quotient 5 and divide the quotient by the number 3, then one can get quotient as 1 and the remainder as 2. Whenever you are taking the integer and dividing by the 3, if you are reaching the number 1, you can stop the process. Now, the base 3 representation is 1, 2, 0. So, 1, 2, 0 is the base 3 representation of the number 15. So, here you can observe that in the base 3 expansions includes the number 1, number 2, number 0. These 3 digits only appearing, no other digits are appearing. Now, for any positive integer x, we obtained the base 3 expansion. Similarly, if the number is not an integer, that means if you are taking any rational or irrational number, how to give the base 3 expansion of the number. Let us consider a number x between 0 and 1. That means every number x between 0 and 1 has the base 3 representation as follows. In the, you can observe this summation and this summation. Here we are starting from 0 to m, this summation running over minus infinity to minus 1 ai 3 power j. The aj's are the any one of the digits from the 0, 1, 2. Now, how to represent any number between 0 and 1 as a base 3 expansions? Consider the number 7 by 9. So, it has the base 3 expansion 0.21, and consider number 1 by 4. It has the base 3 expansion 0.020202 and so on. How to obtain this one? For 15, we are dividing the number by 3 and obtaining the base 3 expansion. There the 15 is an integer. Now, we are dealing with the number in between 0 and 1, it has the rational numbers. So, it is of the form 7 by 9. Now, you can, instead of dividing this number by 3, you just multiply this number by 3. Then one can obtain 7 by 3. So, this 7 by 3 is greater than 1. So, this has the mixed fractional represented as 2 plus 1 by 3. So, 2 times 3 is 6, 6 plus 1 is 7, 7 by 3, it has the mixed fractional representation as 2 plus 1 by 3. So, now this 2 you can write it here. Now, you have 1 by 3. If you are multiplying this 1 by 3 by 3, then one can get number 1. That number we are representing here. So, 7 by 9 has the base 3 expansion as 0.21. Similarly, one can get the base 3 representation of 1 by 4, then one can get 0.0202. It is the repeating pattern. So, it has the alternative representation as 02. So, it is, this number is repeating, we can write like this one. Then the interesting fact is, this base 3 representation 7 by 9 has this base 3 representation and 1 by 4 has a representation as 0.0202 is repeating. Now, some numbers in the interval 0, 1 admit more than one base 3 representation. Let us see the example of that. Take number 1 by 3. If you are applying the process for the obtaining the base 3 representation of 7 by 9, then 1 by 3 base 3 representation is, one can get this one. And similarly, one can get the base 3 representation of 1 by 3 as this one also. For this term and this term, both are equivalent. Okay. So, instead of base 3 representation of first one, one can use the second base 3 representation also. So, if you are taking any number in the interval 0, 1, if it has the form of a by 3 power k, then it has the two different base 3 representation, which is including 1 and other one is the without 1. Now, let x belongs to closed interval 0, 1, then x is the member of the Cantor set C if and only if x has the base 3 expansion using the digit 0 and 2. That means, in the base 3 representation, number 1 will not appear. So, for proving this one, the first place to the right of the ternary point is a number 1, if and only if x between the number 1 by 3 and 2 by 3. Since while constructing the Cantor set, we are started the interval 0 comma 1 and removing the mid part. So, here 1 by 3 and here 2 by 3. So, as per the previous result, if you are taking any number in 0 and 1 by 3 and 2 by 3 to 1, the ternary expansion is different, whereas this 1 by 3 and 2 by 3 has the two different ternary expansion. That means, in the first iteration we are removing the points 1 by 3 and 2 by 3, both has the ternary expansion which has the number 1, whereas in any number of the form a by 3 power k has two different representations. One is given here, another one is we can find from the previous slide. You can see the number 1 by 3 has two different ternary expansions, here one with digit 1 and another one without the digit 1. So, instead of this one can use that this ternary representations. So, the first terma is the interval 1 by 3 and 2 by 3, that means we are removing this interval. So, after this terma is removed, we have the iteration C1, that means C1 consisting of the interval 0 to 1 by 3, the closed interval, and 2 by 3 to 1, and the number 1 by 3 and 2 by 3 each have two expansion, one with the digit 1 in the first place and another one without the number 1. So, they are not removed, that means 1 by 3 and 2 by 3 is not removed, whereas they have two different ternary expansions. Thus, C1 containing exactly the number in 0 comma 1 that has a base 3 expansion not using 1 in the first place. Now, the second place of a number x belongs to C1 is a digit 1 if and only if x belongs to one of the second level termas 1 by 9 and 2 by 9 or the interval 7 by 9 and 8 by 9, these two interval. When these termas are removed, we obtaining the set C2. Hence, C2 contains exactly the numbers in 0 comma 1 that has the base 3 expansion using 1 neither in the first place nor in the second place. So, continuing this way, we see that the points remaining in the Cantor set C are exactly the numbers in 0 comma 1 that has a base 3 expansion not using 1 at all. So, if you want to classify the numbers in the Cantor set, find the base 3 expansions. In the base 3 expansions, digit 1 is appear, then the number is not belongs to the Cantor set, whereas instead of number 1, 0 and 2 is appearing, then we can conclude that that number is belong to the Cantor set. Now, we already obtained that Cantor set C has the all the endpoints in each of Ck. We are starting from C0 and we obtained the C1, C2, C3 and etc. In each process, we have the subinterval. Each subinterval we have the endpoints. So, all the endpoint is the member of the Cantor set. Now, the question is whether we have the any number apart from this endpoint, whereas now we have the one beautiful result, means if a number belongs to the Cantor set, they have the base 3 expansion which including only the digit 0 and 2. So, let us try to find at least one number which is not a endpoint of any of Ck, whereas the number is belongs to the Cantor set. So, for that you can take the number 1 by 4, which we already obtained from the previous slide. The base 3 expansion of 1 by 4 is given here. Here in the base 3 expansion, it containing the digits 0 and 2 only. Therefore, as per previous result, one can observe that an x belongs to the Cantor set C. It has the base 3 expansion using only the digit 0 and 2. Hence, one can conclude that the member 1 by 4 is a member of a Cantor set C. Now, we need to prove that this 1 by 4 is not an endpoint of any interval in any of the Ck. For that, you can observe endpoints are numbers of the form m over 3 power k. Why? Because we are dividing all the interval as 3 equal parts. So, the interval length starting from 3 power 1, 3 power 2, 3 power 3 and 1 by 3 power 3 and so on. Therefore, this ternary expansion either terminate or become all 2's eventually. Therefore, if 1 by 4 base 3 expansion, the expansion is non-terminating and not eventually constant. The digit keeps alternating between 0 and 2. Therefore, 1 by 4 is not in the form of m by 3 power k. So, one can conclude that 1 by 4 is not an endpoint of any interval in any of the Ck. Therefore, the number 1 by 4 is a member of the Cantor set. Now, we already proved that Cantor set has the infinitely many number of points because it has all the endpoints, and now we obtained the number 1 by 4, which is also the member of the Cantor set. So, now just recollect what are all the property we come across for the Cantor set. First, we complete the length of the Cantor set and we obtained the length as a 0. And how many interval we are removed from the interval 0, 1 and obtained the Cantor set is literally we removed all the interval from 0, 1, because in each process we are removing the sub interval with the size 1 by 3 and we obtained the sum of length of the removed interval in the closed interval 0, 1. We obtained the total length is 1. That means, we removed all the interval in 0, 1. That means, the total we removed the total interval in 0, 1 and obtained the Cantor set. So, Cantor set as a length 0, whereas it contains the infinitely many number of points. Now, you can think how complex is the Cantor set, but it is made by the simple regressive process. In the iteration process, we obtained the Cantor set. This Cantor set is introduced by George Cantor, his life spanning from the 1845 to 1918. This is the famous example for uncountably many point has a measure 0. A set has a uncountable number of points has measure 0. Cantor set is the example for uncountable set which has the measure 0. So, the Cantor set is a subset of real number system, whereas it has some complex structures.